Hi everyone, and welcome to the GECCO tutorial on Evolutionary Computation and Games. I'm Julian Togelius.
I'm Sebastian Risi.
And I'm Georgios N.
And we represent the company Model AI and our respective universities, New York University, at the University of Copenhagen and the University of Malta. Okay, so we're going to talk to you about how evolutionary computation can be used in games and for games. So first, a few sentences about who we are. Here you see our faces. This was from just before we gave the tutorial last year at GECCO 2018 in Kyoto. And we, two of us wrote a book recently called Artificial Intelligence and Games, which has much of what happens in here, but we're also going to give you a few papers that, material from a few papers that have been published since. We're also going to give you references throughout the talk to various experimental papers and survey papers we have published. Good, let's get started. So evolutionary computation, as we're in the conference on evolutionary computation, we assume you all know the basic concept about this. And it can be used in games in a number of different ways. When you say games, people often think about playing games as the sort of most orthodox use of any AI techniques. But in fact, we're going to tell you that it's not only playing games. So many other things. It includes generating game contents, for example, levels and characters and quests and so on. Generating complete games, including quests and including rules of the games and assets of various kinds. Modeling players, so you know players' preferences and capabilities. Assisting designers, and probably many other things. I mean, if you're listening here and you're interested in games in general and evolutionary computation, there are probably many other ways in which to use evolutionary computation in games that maybe you will propose and add to this field. So stepping back to history, here we have John McCarthy in the 60s playing chess against a computer the size of his room. I don't know whether he won or whether the room won. But this was very emblematic of AI research in the very first wave. Games were there already from the beginning because people figured out that in particular chess was sort of the apex of thinking, because to play chess you need to plan ahead and you need to plan adversarially, understand your opponent and try to outsmart them. It has been quipped that the first people to work in artificial intelligence, they wanted problems to work on, so they selected problems that they themselves were interested in. And they themselves were interested in playing chess and proving theorems. So that's what the very first AI programs tried to do. Now, people worked on chess for decades and thinking that this was like, you know, a quintessential essential challenge for AI. And then this happened. This is 1997, IBM's Deep Blue computer winning over Garry Kasparov, at the time, the world's preeminent chess player. And this was a big moment of reckoning for the AI community, because what had happened here? For a long time, we had worked on AI and using chess as a testbed, and thinking that people have been saying things like, you know, chess is AI complete. You can't play chess as well as a human master without being generally intelligent. And now you have like a chess computer winning over the best human in the world. And when you opened up under the hood and looked what was there, it was a search algorithm. There was a lot of domain knowledge as well, but at the core of it, it was minimax search. So people started thinking, what's wrong here? Did we choose the wrong benchmark? Are we working on the wrong problem in order to reach artificial intelligence? Maybe there's another game that's important. So people went to Go, which is roughly the East Asian cultural equivalent of what chess is in Europe. Another full information deterministic two-player board game. In 2016, Google DeepMind won over Lee et al. one of the world's best Go players, in an open match that was a similarly big cultural event, and people were like, wow, now we have computers that can play Go. Wow, this is amazing. What now? Have we achieved artificial intelligence? Well, if you looked underneath the hood, there were a couple of neural networks and another search algorithm, Monte Carlo tree search. So maybe these classic board games are not all there is to intelligence. Maybe we need to look wider around ourselves. But before you say that we need to sort of leave games, we are here to tell you that there is a lot of interesting AI problems, including those that can be tackled with evolutionary computation, which is most of them, in the games field. And playing board games is just one small part of it. There's like, there you can do many more things with board games, and you can play many other things in board games, in particular video games. So in most of this talk, we're going to talk about video games, and playing video games, generating video games, modeling players in video games, and otherwise doing things to video games with evolutionary computation and similar techniques. So, how can evolutionary computation be used to play a game? I was just having a sip of tea so you could think a little bit about this. It turns out it could do this in many different ways. So before we get there, we want to sort of first of all dispel a notion. Ever since DeepMind's very public and very famous paper in 2013, where they used deep reinforcement learning to play a large number of Atari games or learn to play them, you might have think that, oh, playing games, the way to play a video game is to simply sort of use deep reinforcement learning. You may even think that surely deep reinforcement learning is the best algorithm for game playing. Well, that's just like your opinion, ma'am. In fact, there are a number of different AI methods that can be used to play a game. We can divide them up into essentially three main categories of methods. You can use planning methods, which require that you have a fast-forward model of your game, that you can somehow simulate what would happen if you took a particular action in a particular state, and you can simulate it fast. Then you can use uninformed search, as in Minimax, Alphabet, and so on, or like simulating search that breadth first. You can use informed search algorithms, such as A-star. A-star, by the way, is everywhere in commercial video games because it's used for path planning and so on, but usually not to simulate the whole game. Or you can use evolutionary algorithms. Then the other main sort of approach to playing games is using reinforcement learning, which requires training time, but not necessarily to have a fast simulation of the game. So here we have temporal difference learning or approximate dynamic programming or many other related algorithms such as policy gradients. You can also use evolutionary algorithms here. In fact, policy gradients can also be seen to be closest to evolutionary algorithms. Third category is supervised learning. It doesn't necessarily require training time, doesn't necessarily require a simulator, but requires play traces to learn from. So learn from examples of other agents or humans, how they have played the game. So you could use backpropagation in neural nets, k-nearest neighbors, support vector machines, or anything from the big bestiary of supervised learning algorithms. You can also, use random controllers to play games or some hand-coded algorithms and so on. What I want to bring your attention to here is that evolutionary computation can be used in at least two different roles to play games, and we're going to talk about both. We're going to talk about evolutionary algorithms in the reinforcement learning role, where you evolve, for example, a neural network that plays a game. We're also going to talk about evolutionary algorithms in the planning role, where you continuously use the evolutionary algorithm to find new plans for what to do, and as you execute them. Just what I just said. You can evolve an agent to play the game through Neuroevolution and genetic programming, or use evolution to play the game as an action selector. Every action you, or every turn you evolve what to do next. Right, Sebastian.
Yes, thank you, Julian. So yeah, as Julian mentioned, one thing you can do is you can use Neuroevolution to play games, but we'll see you can also use it for a lot of different, not only for evolving controllers, but you can also use it to produce content, for example. And the basic idea in Neuroevolution is that you have some encoding of how you transfer your, the genotype to the phenotype. And in this case, the phenotype is this neural network that interacts somehow with the environment. Oftentimes it might control an agent through actions, but it doesn't have to. And then you get a fitness back from the environment that helps you to decide, which neural network should be allowed to reproduce and which one maybe not. And then over time, you get networks that are better adapted at the task at hand. Next slide. Yeah, so here we just have from a review paper we wrote a few years ago, all the different roles that basically Neuroevolution can play in your game. So it's not only about what we normally assume direct action selection. In the top right, you see these different categories, which is, for example, driving a car around, but it can also be used to, for example, modeling player experience, what we will learn more about later. It can be used to select between different strategies. You can use it to state action selection, and also maybe more surprisingly, you can actually also use Neuroevolution to create content in games, like a neural network that, for example, can draw a flower or a particle weapon, or all kinds of different content can be created, drawn by a neural network. And there are a lot of different algorithms you can use for that. You can use, NEAT, CMAS, HyperNeat. There's also a lot of different ways you can evaluate the content. So you can do multi-objective optimization, interactive evolution, or coevolution, incremental evolution. And we'll see some during this tutorial. We see a few examples of these different ways of applying Neuroevolution in games. Yeah. As I said, so you can evolve these neural networks. There are a variety of different ways you can do this. You can use evolution strategies, which has been quite popular recently, also made popular by OpenAI, which allowed really large-scale Neuroevolution networks to be trained with millions of parameters. But then also a lot of the work coming from AI labs also showed you can actually use very simple genetic algorithms as well, and training networks with millions of weights. Of course, most people here probably know about the NEAT algorithm that allows you to not only train the weights of these networks, but it's also one benefit of evolution is that you can optimize both the topology of the network and the weights basically at the same time. So you have neural architecture search in a reinforcement learning like setting. And then other approaches, we'll talk about them a little less here, is also indirect encodings have been quite popular in the past, like HyperNeat, compressed weight space. One thing we will talk about, a new way that we didn't write in here, but data-driven encoding. So can you learn an encoding from the data itself, which is particularly relevant for games? And we'll talk about that later in the context of this idea of latent variable evolution, which is a quite new technique. So why should you care? Why Neuroevolution? So it has a few kind of nice properties. It's broadly applicable. So as I said before, it's not just about training a controller. You can use it to create content. The nice thing is it can be used for both supervised problems. If you have the target pattern, you can use it for that. But it can also be applied similarly for RL problems, and doesn't require your network and everything to be differentiable. What you normally have to take care of if you work with gradient descent-based techniques. There exists a wide variety of methods for diversity, encouraging diversity, which is especially important if you want to create game content, you can bias neuroevolution to create a large variety of different interesting content that might vary across some dimensions. So for example, using Metal Lead's algorithm. There's a lot of interest in open-ended evolution and open-ended learning. So can you set up a system that constantly produces novel, interesting things, which is of course also important for game playing, for players to keep engaged. And maybe most exciting for me, I think that it also enables kind of totally new types of games. So games, that would not be possible with classical AI methods, but actually using evolution and neuroevolution allows you to create games that would have not possible before, and that actually allows also very novel gameplay mechanics. By the time that this tutorial is probably shown, we're also currently writing a review paper on new mechanics that are encouraged by including a neural network. So we'll add that as well. Okay. So just a few examples that quickly go through, just so you get a broad overview of different types of, for example, games that it has been applied to. So this is a famous example by Stanley et al. From 2005, where one of the earliest example where you use evolution and specifically neuroevolution to create a completely new type of game. So in this game, you kind of you evolve these two armies, and you can actually guide the fitness shaping of these armies. So you design the environment. You can say, first you train it against a simple enemy turret, and then you add, for example, another one. Then you make these more complicated by allowing them to move around. And when you have your perfect, basically, army trained through this evolutionary process that you can control, then you can pit it against another person's team and see who wins. And so basically the whole game was built around the concept of doing this kind of incremental evolution, reward shaping, being able to change the fitness function in real time, and then having this real-time evolutionary loop that allows these units to adapt to those changes made by the user. Okay, next. And then we were building on this with Daniel Yalov and Julian and myself. One thing we did in this EvoCommander. So in NERO, once you trained your army, basically you sit back and observe, the two armies battling it out and seeing who wins. And what we were interested in is, can we still keep the player engaged while the battle is going on? So in this game, EvoCommander, it's another example of a new game mechanic. You evolve these different brains that are responsible for different behaviors. So you could evolve, you have these two tanks battling each other, and you can evolve, for example, one brain that's responsible for melee behavior. And you can evolve another network that's responsible for, long distance shooting of grenades. And then, so you evolve these before you go into battle. And then in the battle, you can dynamically, as the player, switch between these different brains, different neural networks that you evolved. So you have to decide, on the one hand, what type of selection of neural networks of behaviors you want. And then during the battle, you still can switch between which one should be active at which point. So this allows the player to stay more engaged also while the battle is basically going on. And here you see how players can decide. So you have these sliders where you can decide on, for each of these brains that you evolve, you can have these sliders that say how important should certain properties be. So should it stay close to the enemy? Should it stay far away? How important is precision? How important is that you get inflict a lot of damage? And of course, you have to balance this because if you want to optimize for everything, and you might not get a really good solution. So you're trying to specialize these different neural networks that you evolve to be fit for the strategy that you want to pursue. And here you see how you can use this concept of basically incremental evolution. So first, a player, for example, created a neural network that would just face the target. And then based on that, you see this family tree at the bottom. You can further create a network that would go to the target and then hit the target. Or you can, from this face target, you can also directly evolve a network that would shoot the target. So you can basically, building on these stepping stones that you evolved, you can create more and more sophisticated behaviors. So this was one example. Of course, the other thing I mentioned at the past, what's probably most known for in general neural networks is this direct action selection. So the network gets some kind of information from the environment, which can be, more recently it's giving the network directly the pixels. Previous approaches, just as NERO, what we see at the bottom is that you get some kind of pre-processed information. So you get like the enemy radar is like rangefinders. You get a sensor if your aim is on target. You have object rangefinders. So there's some more pre-processing going on in these approaches that don't directly work from pixels. But now actually Neuroevolution has been shown to also work directly from pixels in 2D and recently also 3D games. So yeah, there are different input representations. So you can have straight line sensors, pi slice sensors, angle sensors, pathfinding sensors. Of course, there can also be third person inputs like the number of in Pac-Man, the number of pills that you ate, and so things that don't have a spatial component, your health bar, these type of things can of course also be part of it. And then of course the raw sensory data, as I said before, is also more recently used. And now Julian will go through some more example on how you can use this in a car racing domain.
Thank you, Sebastian. So yeah, so tying on to the input representation, and you're going to see direct action selection with evolved neural nets in a car racing domain. So let's preface this that this is old stuff. I mean, this is from back when I was a PhD student, and the graphics are similarly old, but I like to show this example because it is very instructive and it has some fun videos, which people tend to like. So driving a car fast requires fine motor control. Get it? Motor control? Or so I've been told. I don't really drive. But car racing is actually a pretty interesting problem because it has several challenges. Apart from the very sort of fine grained control, you need planning to overtake, you need planning to figure out a racing line, and even adversarial planning if you are trying to get past other cars on the road. And you don't know what they're going to do, you need to try to predict it. So it's more complex than it might seem initially. So for my PhD back then, in 2005 or so, I developed this simple car racing game which was intended to qualitatively replicate a simple radio-controlled car game. You had these bang-bang controls. You can drive, you could accelerate, decelerate, turn left, turn right. You have solid walls. Here's the car is the red thing. Waypoints must be passed in order. You see the waypoints 1, 2, 3, 4, 5, 6. And the fitness is a continuous approximation of how many waypoints you passed in about 40 seconds, I think. And then we had a neural network. Actually, this is a schematic representation. It had, in fact, 9 inputs, 6 rangefinder sensors, a waypoint sensor, speed, and a bias input, 6 hidden layers, and then 2 outputs, one which is interpreted as thrust, if you're neutral, accelerating or braking, and steering, the other one, neutral, left or right. The inputs, the rangefinder sensors, if you see here to the left, you see rangefinder inputs. These are the cyan things that are like in a fixed configuration. In other versions of the experiments, we evolved the direction and the length of the rangefinders as well itself. Think of them a little bit like, they were meant to replicate things you could put on a robot, like infrared sensors, for example. But you can also think of them as like the feelers of a little insect or something like this. And what I return is a distance to the nearest wall in that direction. We used a very simple evolution strategy. This is a mu plus lambda evolution strategy with no self-adaptation. As you see, we're basically sorting the population of fitness every time after randomizing it. And then replacing the worse half of the population with the better half of the population, or copies of the better half of the population, and then mutating the copies, adding Gaussian noise. This is extremely simple, and like this is a pseudocode, and real code in Java isn't much longer than this. Real code in Python is probably about this long. So here's an example video. 50 plus 50 evolution strategy, 100 generations. That's 10,000 evolutions in total. And you seeing this car learning to drive. And it could already drive on its own about as well as any human onlooker. I could maybe at some times match it, but I don't think I could ever beat it, because maybe it wasn't optimal, but it was like for practical purposes near enough. So maybe this version of the problem wasn't very hard. Now, what we then looked at was, can we take this controller, vote for this track, and try it on other tracks? What would happen? And it turns out, in general, it doesn't work at all, or it works very badly, because it has learned a policy that really just works for this one track. This, by the way, this is a general phenomenon. It's not only limited to Neuroevolution and not only limited to car racing. This kind of overfitting is even more severe in the very common deep reinforcement learning benchmarks that we have these days, such as the ALE benchmark. So how do we achieve more general game playing skills? And is there a trade-off between generality and performance? Can you be both a good play well and play across a large number of tracks? To investigate, we set up a couple of different tracks. You see that some of these appear to be identical, but they're not. So the first 6 tracks are 3 tracks and their mirrored counterparts. So the same tracks, but the waypoints are in the other way. Which is interesting, because if you learn to play on the first track there, then the second track, its mirrored counterpart, you can't play that, because it's only learned to turn left, essentially. Or it's one turn, it has to turn right, but it does that much less. You sort of need to train on these separately. Now we thought, how could we train a neural network that can train all and could drive on all of these tracks? So we turn to what is called incremental evolution. This is a good idea. Usually is rediscovered many times by different people. This is also in the reinforcement learning community known as curriculum learning. The idea is that you change the fitness function to make it more demanding as soon as a certain fitness is achieved. So you introduce a more complicated version of the problem. In this case, we add new tracks to the fitness function as soon as the controller can drive 1.5 rounds on all tracks currently in the F set. So as soon as it can drive on average 1.5 rounds on 3 tracks, then we add a 4th track to it. And what happens? Well, what happens is that we get this interesting fitness graph. Presuming you can see my mouse pointer here. We see the fitness going up. It's still training on one track until it reaches 1.5. We add another track and fitness immediately drops quite severely. And then it learns to sort of drive decently well on both tracks, going above 1.5. Adding a 3rd track, fitness drops. Adding a 4th track, fitness drops more. And then it keeps going until it's somewhere here, around 500 something generations, learns policies that can drive on all 8 tracks, and then it keeps getting better. So here we see this neural network navigating a complex track. This track here is really hard to drive for a human. Or, I mean, you can, but you're almost certainly going to drive slower than this one. It is also a track that if you try to train a neural network from scratch with no previous knowledge to drive on this track, it won't be able to do it because the rewards are too sparse and the whole landscape is just too deceptive. So it's a pretty interesting method we found here. So thinking that this was successful, we moved on to the next part, because usually when you race, you don't race alone. You have other cars on the track. That's sort of the point of a race. So we tried just putting 2 cars with controllers that were evolved on their own on one track. and see what would happen, and it was a disaster because they couldn't even see each other. They didn't even have sensors to see each other. That's easy. It's easy to basically add sensors, car sensors, to see each other. But how do we train them? How do we train controllers that take other drivers into account? Avoiding collisions or even using the other drivers to their advantage. So one solution here is to add car sensors and then and they work just like the rangefinders and use competitive coevolution. In fact, I've been at 41 years old, I've been trying to learn to drive over the last years and so on the streets of New York and New Jersey, and I'm seeing a lot of these situations happening here where people might try to avoid collisions, but there's a lot of like strange foul play. Competitive coevolution is a common concept that comes from evolutionary biology, and it's what explains these very strange shapes in nature, where you have flowers that look like, you know, vases with a nectar hidden away deep into some strange little tunnel, and then you have birds with long beaks, in particularly evolved to sort of sip this nectar. So, and trying to replicate this in the computer involves that you evolve at least two individual, and one individual success is adversely affected by the others, directly or indirectly. And this is very potent. There's been some brilliant examples in the literature of using competitive coevolution to great effect, such as Hillis' 1991 evolution of sorting algorithm, sorting networks and sorting problems. But it's also played with lots of problems. Competitive coevolution is a field which is very interesting, but hasn't made a lot of progress recently. It is also, by the way, the same basic idea as you see in generative adversarial networks, only here we use evolution instead of gradient descent. We use a standard 15+15 evolution strategy. In each individual is evaluated through testing against the current best individual in the population. Now, the question is the fitness function. When we trained a controller to drive on its own on a track, we used absolute fitness. So basically, how far did you get in 700 time steps, which is 40 seconds or so. But in a real car race, you're not really just trying to be fastest. Above all, you're trying to come in front and get in front of the other cars and be the first person to sort of, get to the goal. So you can also define relative fitness, which is the distance ahead of or behind the other car you end up in after n time steps. Now, while I'm taking a sip of tea, I want you to think about, is absolute fitness or relative fitness the best choice here? How would it shape their behavior? Let's see. Here are two cars evolved with absolute fitness. As you can see, there was a little bit of a scuffle in the beginning, but both of them are essentially driving very well. And yeah, that was like a questionable turn there by the blue car, but they are driving fast, getting around the lap, not really sort of doing anything unusually adversarial. That's nice. They just focused on the target. Red car is clearly winning, but hey, someone's gonna win. Now let's see what happens if we evolve them with half absolute fitness and half relative fitness. So they get a combination of how far they got to the track and how far ahead of the other car they ended up. Then you get this interesting behavior. Wow, starting to look like New York taxi drivers. And that was a nasty move by red car, but blue car is still in the race. So you see it's much more sort of adversarial and collision oriented. Now let's see what happens if you use only relative fitness. Yeah. This is not nice, right? Where these people get their driving licenses. Finally, blue basically got his revenge on red, and then he doesn't care anymore because he's already in first place. Why bother? Right, so what we can see from these is that you can you can do a lot of, you can use these fitness functions to shape the behavior of the agents in many different ways. And this could be very useful in developing agents for commercial games, for example. Now, another thing, I promise to tell you another way of using evolution to play games. We were talking about the evolutionary reinforcement learning setting. Can you use evolution to plan? So some games have extremely high branching factor. Chess has an average branching factor of 35. Go has an average branching factor of 350. Branching factor is how many different actions you can take each turns. And it took 20 years to go from Grandmaster chess playing to Grandmaster Go playing, largely because of the extremely different branching factor. Now, if you look at Civilization or StarCraft or so on, say you have 10 units, which can each take one of 10 actions every turn, or like, you don't really have turns in StarCraft, but every sort of frame, then you have a branching factor of 10 to the power of 10, which is clearly absurd. You can't even begin to search it. Tree search methods like Minimax and Alpha Beta and Monte Carlo tree search can't even get past the first fly. So our solution here from evolutionary computation point of view is to treat the whole plan as a sequence of actions and the value of the final state as fitness. So we're going to see in the game Hero Academy, which is a relatively simple strategy game, which is available on the iPad. You need to win over the other players' armies, either by defeating all their units or capturing their crystals. And every turn you have 5 different actions that you can distribute among your different units. So we tried using Monte Carlo tree search to play this game, and it's extremely bad at it. It beats random, but it doesn't even beat like a version of depth first search. So a greedy search on the turn-based space or on the action-based space. So like very trivial, simple algorithms, which basically translates to we don't have an algorithm that plays this well because of the branching factor. The idea here we came up with was to use online evolutionary planning. So every turn you evolve the set of actions to take next. A chromosome, which you evolve, is a sequence of 5 actions. And you use a simple evolutionary algorithm, so standard like mu plus lambda, 50% elitism, random selection parents, uniform crossover, 10% mutation rate. And here's an illustration of what it looks like. These are 2 individuals at the top, 2 different chromosomes, where you see the heal, move, attack, 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 with here's 1 chromosome at the top, and for each move you also see who you're moving from and to. And here's another one, and here's the recombination operator finding a new chromosome from these 2. And it turns out that evolutionary computation very drastically outperforms everything else we have. Even though it evaluates fewer unique outcomes, fewer unique sort of move sequences each turn, but it just searches the space efficiently because it does not get stuck on the first few plies like Monte Carlo tree search and every other tree search algorithm does. This is an interesting example because there are many real-life problems which are like multi-action games. Right, now we're going to transit away from playing games and talk more about procedural content generation, using evolution to create parts of games. These are some examples of famous games that use procedural content generation. Here you see Spelunky, a 2008 indie platformer, where it's basically Super Mario Bros. Meets Indiana Jones. Every time you play it, you have a completely new set of levels. They're generated as you start each playthrough, which forces you to actually learn to play the game, not the levels. This is one of the games in the Civilization series, arguably the best games in the world ever, where you start by ruling a Stone Age tribe and then trying to build a civilization to last for thousands of years and potentially take over the world. And a couple of other games, Elite here in the background, which is like a famous space adventure game from the early 80s, which was famous because you could visit thousands of stars and their space stations and so on, even on computers that were extremely limited, because it generated whole star systems and everything in them as you played the game. So why would you generate game content? There's a number of different reasons for doing this. You may want to think that, hey, you want to replace the game designer, and not have to pay the game designer, which is what I started out thinking a long time ago, but it's not that easy. It's more meaningful to think of this as assisting building tools that can assist the human designer. But as Sebastian mentioned earlier on, it's also a way of making new types of games possible that couldn't have been done without game content generation. Maybe to go beyond human creativity, see if algorithms can come up with things that humans could not come up with, and or to really understand game design. Because if you create algorithms that can design a game, then you have sort of a working theory of what the design of this game looks like and what the design process looks like. And evolutionary computation applied to PCG is called search-based PCG. I'm going to hand over to Sebastian here. Sebastian, do you want to share from your side?
Yeah, let's see if that works.
Yes.
Okay, can you see?
Yes.
Right, so yes, so we talk about search-based PCG, and yeah, one really popular way of searching this space is evolution. And we have a few different examples here of the search-based PCG paradigm. You can search it you can use it to search, for example, for different weapons in this game, Galactic Arms Race, different particle weapons. You can search, very popular example is different levels in Mario that satisfy different player constraints. So for example, you might want to search for a level that has a certain difficulty. Then also Julian and Wishwituba had some early work in not just evolving the levels, but actually the roots of the game. And then Georgios, I think, is going to talk a little bit about later how you can also use this in the mixed initiative content, where you have a human and a computer designer that can complement each other. So now I want to talk a little bit more about PCG approaches that use actually neural networks in the generation of content. And so one example that we worked in back in like 2015 and before, when I did my PhD, is this game Petals, where basically each flower in this game is generated by a particular type of neural network called the convolutional pattern producing network. And the idea here also was can we design a game around the concept of producing content and about the concept of using simulated evolution. So really briefly, I'm not going to go into too much detail, but basically this, you have a neural network. In this case, this is evolved by NEAT. So that determines both the architecture and the weights of the network. And the network basically can paint a flower. And you can evolve the network. So different networks will produce different types of flowers. And so we thought this could be a nice game idea that basically allows anybody to breed the flowers they find particularly interesting. So when you click on a flower, you get this offspring that you see here by slightly mutating the neural network that produced the flower. And then you can decide to plant that flower. And so over time, you can basically personalize your balcony based on the flowers you like. You can even share these flower seeds with other people, or you could on Facebook. Now it's not running anymore, but back in the day, you could automatically share those and then continue basically an already evolved lineage. You can continue that lineage. So enabled by neural networks and evolution, it allowed a kind of new type of gameplay that allowed unlimited variety of different flowers. So this was one example where we had to hard code the encoding the neural network to produce flower-like images. But what if you could just show the network, for example, a bunch of flowers, and then it only produces flower-like images or other type of content? And so this is basically one idea behind this idea of latent variable evolution, which is a more recent idea of how to create content or in general artifacts, where you train a generator, which could be a generative adversarial network, or it could be a variational autoencoder on existing content. So it was first introduced to produce artificial fingerprints in Julian's lab, where you train it on these existing fingerprints, and then you can basically search the space of what this autoencoder, this generator, learned to find fingerprints that have certain properties. For example, unlocking a lot of phones, which is one property you might want to search for. You can also combine it with actually interactive evolution. So you train it on the right side, you train it on a bunch of shoes or faces, and then you can, by only evolving this latent variable that goes into the generator, you can actually guide the process. So the advantage is that you get content that you're interested in, and you, like in this case, for example, shoes, and you don't have to manually tweak the encoding to only produce shoes. So this is particularly interesting also from the perspective of games, where oftentimes you already have a lot of content available. So for Mario, we have a few levels. For games like Candy Crush, we already have a lot of levels. So can we take advantage of this knowledge that's already existing in these levels to create new levels? So as I mentioned briefly, one neural network that you can use for this is a generative adversarial network. Also not going to go into too much detail, and maybe most of you already know how this works. But basically you have this, you have this generator network, and you train this generator that normally it gets random noise and produces, at the start a random image. And at the same time, you train this discriminator to determine if the produced image is a real image or a fake image. And so both of these systems get better over time at producing content, but at the same time, the discriminator gets better at saying this is not real. And so as Julian mentioned, this is a kind of co-evolutionary process where both these systems play this kind of minimax game against each other and getting better and better. There have been a lot of advancements recently that now you can basically not distinguish, or it's really hard to distinguish the artifacts generated by these GANs from real images. Like, for example, these faces do not exist, but were actually generated by a GAN. And so in work we presented at GECCO in 2018, we thought, oh, this could be great to also apply for games. So the basic idea is you train a GAN on a lot of existing levels. And then after you done the training, so it works in these kind of two phases. So in the first phase, you just train again on existing levels. Once you're happy with this, you can throw away the discriminator and you only keep your generator. And while you normally would just feed a random vector into this generator, what you can do with this latent variable evolution, you can search this latent vector with evolution to find levels that have particular properties. So one could be, for example, difficulty or solvability. And so this is what we did in this GAN approach, that we trained it on 173 level segments. So just small level segments. We were cutting the whole level in these small segments, training again on it. Here's just the representation we used. So we didn't use the pixels, but we used this level representation, this tile-based level representation. So each tile can either be like solid or breakable, or it can be different types of pipes. At the bottom, you just see the design of the generator and the discriminator. So just again, architecture designed for these kind of tile-based games, but we'll later see it's not only restricted to Mario, you can also use it for other games, just as Candy Crush. And then we basically use CMAS to just evolve these, the much smaller, I think it was 32-dimensional input that goes into the GAN. And then you can use CMAS with this pre-trained fixed generator to, for example, optimize for the number of ground tiles, or you can optimize a certain level of difficulty. Like, while difficulty in this case would be, for example, less ground tiles, so you have to do more jumping and more enemies. So we tested this kind of target-based evolution. We also tested an agent-based approach where the fitness, we have this A-star agent by Baumgarten, and then the fitness was, the percent of the level that's playable plus the number of jumps. And you see an agent on the right side. And then we just wanted to see, is it a good representation that you get out of this? So one thing we might want from our genotypic representation is have some kind of level of, can it capture these domain regularities? And we see here that if you put a random vector in, you get different variations, which is important if you want to run evolution, that you don't just get the same, pattern out. So it is able to generate different levels of variation, and it is able to capture common domain regularities, like there should always be ground tiles and there should be these pipes. Of course, sometimes you also see some artifacts. It did not always perfectly capture the pipes, so you sometimes see these broken tiles as well. And then what you of course want for, if you have an evolutionary algorithm, you want it to be there's some locality. So if we take the parent to the left and then apply Gaussian noise to the input vector, the 32-dimensional vector, we want things that vary, but also don't vary too much, so you can efficiently search that space. And as we can see here, we get actually levels that vary, but there's also differences in what the GAN expresses. So that shows that it looks like it's a good genome to phenotype mapping that you learned in this data-driven way without you having to design it. And here on the left side, you just see the evolution going on. So initially, it doesn't produce anything useful, but over time it gets better and better. On the right side, you see the fitness. Lower is better. So it's getting better and better, producing levels with a certain fitness property, for example, level of difficulty. And here are just some selected examples where in one we wanted to maximize the number of jumps on the left side. So you can see it's a level where the agent has to jump a lot. On the right side, we wanted to minimize the number of jumps, and it only requires 1 jump to complete this level, to jump over the enemy. And then of course, you can not only apply it to these overground levels, but you can also train again then on, for example, underground levels. And again, it captures the regularities in this domain. For example, in the overground levels, you see that there's always a ceiling covered with tiles, which it can reproduce as well. But you also get levels that are not only in the training set. So it's not just reproducing existing levels from the training, but it is creating variations on these themes that were in the training data. And here you see, going from the left to the right, it's actually increasing difficulty. So the segments it plays get increasingly complex. And so one advantage of this method is it's really fast. So CMAS runs in less than a second. So you could even use this, what we want to do in the future, to generate levels on the fly that have the right difficulty. So if it sees the player is struggling, it could reduce difficulty. If it sees players perform well, increase it. So then this paper just accepted at COG, which was a collaboration between our company Model AI and King, a research collaboration. We thought we can apply the same approach also to Candy Crush levels, because there is a lot of Candy Crush levels already out there. And we think it makes a really interesting domain. And it's actually quite complicated, because you don't have just to capture these local patterns that we see in Mario, like how the pipes are composed, but actually it is more complicated that you also want to capture global patterns. Like a lot of the levels have some kind of level of symmetry. And so it's actually a quite hard test domain for these PCG and evolutionary algorithms, where there's a lot of room left for improvement. So we saw that that it is able to also generate, with some modifications to the algorithm, it is able to generate symmetric levels, but that ability could definitely be improved by, for example, trying out other approaches like self-attention GANs or trying chord-conv GANs. So different variations of these GANs and latent variable evolution could make it even work better. But now we have the nice music, but this is a level produced by a generative network. And we can see that, maybe it doesn't directly look like a computer generated level. The other thing you can do, what I briefly mentioned at the start, you can also use it in an interactive evolutionary setting. And so an advantage of this is that, especially when you do interactive evolution, where basically the user can guide the path that evolution should take, there is this problem of user fatigue. So a lot of times evolution will produce something that might not be, work that well, or might not be that nice to look at. So in interactive evolution, it's good to keep the number of iterations down, the number of times the user has to do something, because quickly you run into this problem of user fatigue. And so the benefit of here is that when you do interactive evolution with this latent variable approach, is that all the content you get is basically reasonable, okay content. Nothing is like a completely random, for example, Mario level or Zelda level. And again, you just evolve. What you evolve is this latent vector that goes into the GAN, and you can guide basically the type of levels you want. And so we tested this. There's a paper that will present in more detail also at this year's GECCO, where you can do this interactive evolution, but you can also change the sliders directly, the sliders determining the latent variable that goes in to fine tune your levels. And we found that this combination works quite well. And now I give over to Georgios, who will talk also more about how you can, some mixed initiative approaches where you have both the designer and the computer kind of working together.
Thank you, Sebastian. Let me try to share my screen.
Maybe I have to stop share. Stop share.
Right. So basically, so far, Julian has mostly been talking about playing games, AI that plays games, and then Sebastian went into the content generation process. I will be continuing, as Sebastian said, on that front, on that role of AI. Then I will be finalizing the talk with AI methods and approaches for modeling players. So let me pick it up from where Sebastian left it in interactive evolution, and just talk about other paradigms within content generation and the use of evolutionary computation within content generation. Here I give you an example of how we utilized simple evolutionary strategies to generate two-level, in the procedural generation fashion, two-level first-person shooter domains, let's say levels, right? So we visited the literature of popular design patterns within procedural, within first-person shooters, such as, first-person shooters should have two levels. They should have particular areas where you can cover yourself. They should have sniping locations and so on. So it was like some form of multi-objective evolutionary approach. We optimized for all these parameters. We end up with levels like the one that you see here. But it's important to note that games are not just levels. There are so many facets of creativity within games that we can actually use evolution to generate or evolve. There are visuals, which could be photorealistic or abstract. There is audio, there's music generation going on, and sound effect generation. There's obviously narrative generation. Gameplay can be seen as a form of a creative process. Game design, of course, like Julian's example back in the days, where you can evolve rules in simple Predator games. And obviously we talk a lot about level design. So one of the important things that has been recently looked at within the literature of procedural content generation and evolution is what we call orchestration. So basically the process that you can use evolution or other methods to put together the generation of more than one creative facet. Like, for instance, generate a level with the corresponding rules, or generate visuals with corresponding sort of sounds. In this particular example that you see in this slide, basically we co-evolve or sort of fuse the creation of levels with weapon generation. So basically, on one end, we have a convolutional neural network that processes game levels from first-person shooter games. And then on the other end, you have a number of parameters that represent weapons in those levels. So by fusing them with let's say a multi-layer perceptron at the end, what you can achieve is that a particular level designer, let's say, might just only want to create a level for a particular first-person shooter, and then the common representation that we see here can actually provide a weapon that makes this particular level as balanced as possible. So it's basically a common representation of balance between weapons and levels. So you can just create a weapon and the system can give you a level that is very well balanced for this weapon, or the other way around. Now, another very popular paradigm and very useful for game development and game design is what is called mixed initiative co-creativity, or mixed initiative procedural content generation. So the way to view this is like a spectrum between human creativity and computational creativity, and the initiatives that each one of these actors in this sort of dialogue take. So you can have systems that require the full initiative of a human, like let's say the Unreal development kit, all the way to systems that allow only limited interaction from the human, like for instance the speed tree, which only allows humans to play with a few parameters within a computational creativity sort of dialogue with speed tree. So we will be looking at other parts of the spectrum very, very soon. But then one more thing to say about creativity in general, both human and I guess computational, is that it is an iterative process. And we see that through interactive evolution, through the examples that Sebastian gave. But, you know, in a sense, we're trying to emulate how humans create. And what we often see, like in this example, this image from Persepolis here in Iran, is that different actors, different architects or sort of artists take care of different parts of a creative process in an iterative fashion. So in that sense, we try to simulate that and bring that into games and use evolution to actually create in a similar manner. So one of these weird ideas we had back in the days with Julian, which is I would say an early version of what Sebastian was talking about latent variable evolution, an early version of that that meets somehow quality diversity because it fuses, let's say, constrained novelty search with denoising autoencoders, with compression mechanisms, is basically the idea that you know, you have a system that generates content like spaceships that gets trained on, and then basically we use that training set and we use the latent vector, let's say, that has been developed through the transformation phase, through a denoising autoencoder, through a variational autoencoder or whatever, and then we evolve using neat and constrained novelty search. We generate by evolving new spaceships that are as novel as possible. And we keep doing that in an iterative fashion so that we eventually we come up with more novel and complex spaceships or levels or whatever else we might want to evolve. So this was one of these sort of weird ideas that actually gave input to quite basically fuses the idea of having a system that generates good quality content in games, but also quite diverse for designers to pick and get inspired from. So this is another example from work by Antonis Liavis, myself, and Julian, which we call the map detailer or sentient sketch world, where it comes in line with what Sebastian was talking about. It is an interactive evolution process, but in a creative, requiring a higher degree of initiative from the designer. As you see, at each interactive evolution step here, the designer can go into the map that is generated and fix bits and pieces. And every time there's a new interactive evolution step, there's a finer degree of resolution that is provided by the system. So this system uses some sort of hybrid between backpropagation and novelty search. Another example is what we call the Sentient Sketchbook, and it's again a mixed initiative toolkit for designing strategy maps. Initially, the designer places some high-level sketch, let's say, designs a high-level sketch here on the left of the image, let's say, of a strategy map. So what you are able to see is a number of resources, a number of bases and impassable areas. On the right of the map, what you see is a number of recommendations provided by evolution. It's basically, you have a system, you have an algorithm that sort of looks at the sketch of the designer and generates, evolves levels that they satisfy particular objectives. In addition, the recommendations also evolve levels that they're as novel as possible, given the designs of the and the sketches of a particular designer. So yet another example of how you can use interactive evolution in this sense, or mixed initiative co-creativity in this particular sense in games. Now, you can of course use novelty search to come up with suggestions about content that is as novel as possible, but you can also use a form of temporal novelty search that we call surprise search to actually deviate not only from what you have seen in the past, but also temporally deviate from what you're generating. So basically, what you're doing there is a number of populations that you generate, and then you somehow come up with a compressed representation of those. You come up with a number of K behaviors here, and because you have seen the history, you can come up with a model, a predictive model of where the behaviors or the content that you're generating is going to go in the next generation. You have the expected behaviors of the next generation. You actually have the actual generation, and from the difference of these two, from the delta of these two, you can come up with a model deviation and come up with a surprise score. So basically what you eventually want is that your evolutionary algorithm, your divergent search algorithm, creates as surprising content as possible for, in an autonomous fashion or in a mixed initiative fashion. So we have seen how good surprise search is for generating really robust and efficient and diverse behaviors within simple robot navigation tasks. What you see here is like how well surprise search is basically distributing, explores the search space, the behavioral space in this particular case. And we have seen how well it can actually do with generating surprising content, like surprising weapons in this particular game, for instance, like this one. This is really a weird weapon for a first-person shooter. It's like a landminer, something like that. So basically, by evolving particular parameters of a weapon that appreciate particular and satisfy particular constraints of the game, like a balanced level, we end up with really interesting results like this one. Now, obviously, surprise search has been doing very well with other within other domains. Beyond games, we have been seeing some really good results when it comes to both diversity and efficiency of robot morphology, for instance, evolution, and maze navigation. And especially if you combine surprise with novelty, you come up with really interesting and robust results. And so you end up with surprise as an element for what is called quality diversity. And I'm sure that many of you here are familiar with the term of quality diversity. Briefly put, we're trying to generate a number of good quality, but at the same time, diverse solutions for a particular problem. And with Julian and a number of other authors here, we came up with a review paper last year about the benefits of quality diversity for procedural content generation and the few examples that already exist in the literature. You saw the sentient sketchbook example, for instance, and the surprising weapons example. Have been some examples with Mario levels and some Hell Bullet games that levels that have been generated through quality diversity through various approaches, varying from map elites to constrained novelty search or novelty search with local competition and so on. Right, so I'm jumping now. We're basically done with content generation. There's so much more to discuss about content generation, but because we don't have time, we're moving into the last role that we are covering here with regards to AI in games, and in particular with a particular focus in evolution and evolutionary computation. So player modeling, if we want to look at it in a nutshell, is basically the process, the computational process of mapping some particular aspects of a player and the gameplay interaction to some form of, let's say, some annotated data. This could be behavioral data. This could be aspects of gameplay behavior. They could be also annotated labels of experience, like, sad faces or frustrated players and so on. Now, with regards to the input, there's so much one could do. Some good ideas is basically to fuse the various forms of these really complex spatiotemporal signals that you get from players that vary from gameplay metrics to physiological sensors to facial expressions to the pixels of these facial expressions and so on, that vary over time, and you can treat them through variational autoencoders or any other sort of compression mechanism, and end up with a latent space that you can use to process in order to be able to predict behaviors of players or experiences of players. With regards to the output, and because we're talking about players and because we're talking about experiences here, there's a long sort of discussion within psychology, behavioral economics, neuroscience. How do we value experience? What sort of number do we give to subjective notions such as experience? It's a long debate that I don't have time to actually go through, but the two major schools here is on one end that we can actually do that with numbers, and on the other end, the other school is suggesting that no, we cannot really represent subjective notions with numbers. We can only represent them in relative relationships. So recently within the affective computing community, which is the community that studies emotion, affect, experience, and so on, there's a new paradigm that is called the ordinal approach that is sort of taking traction, which actually views all annotations that are provided by players, designers in this particular case, of subjective notions such as experience as an ordinal process, right? So they would call it an ordinal approach. And what you can do within AI to actually deal with these ordinal labels is to basically treat it in an ordinal fashion. So I'm giving an example here of Julian being frustrated if he's treated as if he's treated as through a classification problem. Julian could be 0.86, whatever that means, frustrated. So we could treat this as through a regression problem, and we can instead look at Julian's frustration from Georgios' perspective in a relative fashion, and it turns out that the last approach of looking at subjective notions such as frustration is the better approach. Why is it better? Because it gives you more reliable models of experience. These models tend to be more general, and they also give you higher degrees of reliability. So you can actually trust those models and trust those annotations more than anything else. Right, so how do you do that? You do that through a subclass of supervised learning, which is called preference learning, and it's basically inspired and built upon our ability to express preference directly in terms of specific subjective values. And there's a long and big volume of papers and books about the topic. One good book is the one that I'm citing here, Working with Preferences, Less is More. So if you're interested more in preference learning, you can start from there. Now, obviously, you can view preference learning from a deep learning perspective and talk about deep preference learning and look at any supervised learning approach that you're familiar with through a preference learning lens. So basically, you can look at neuroevolution as a way to evolve neural networks that would be able to predict ranks or predict preferences, or alternatively, you can go into standard gradient search, stochastic gradient search, and so on, and talk about RankNet, or even SVMs, decision trees, random forests, and so on. Now, one of the things that we did, one of the interesting studies within preference learning, we did in collaboration with Ubisoft within Model AI, the company that we are affiliated here with Sebastian and Julian, is to look at gameplay data from players of first-person shooters like Tom Clancy's The Division, and try to predict their core motivation values, which are derived from the self-determination theory like a couple of decades ago. So there are three, as you will see, three factors from motivation that we try to predict, and these factors of motivation are derived from questionnaires that we got from Ubisoft. So basically, what we try to do is to map between what you do in a game and what is your degree of competence, autonomy, relatedness, and presence, as you will see. And it turns out that you can do that with very high degrees of accuracy. So you can just tell whether players are motivated or not just by looking at their gameplay data. And this is a short video that actually depicts the procedures. So we have like 4 factors I was talking about: presence, competence, autonomy, and relatedness, derived from self-determination theory that we're trying to predict through preference learning based on particular, very few actually, gameplay features that we got from Ubisoft for the game Tom Clancy's The Division. Now, the next question that comes into mind is whether you can do such a thing not through some sort of processed, ad hoc processed information that you get from players, but directly from the pixels of the screen. So the assumption here is that when I look at the screen, when I look at the gameplay session, I can actually look at the emotion of the player, because the emotion of the player, the experience, is already embedded in that sort of interaction, right? So we just put that assumption into the test, and we used simple games like the one you see here. We used a number of different convolutional neural networks, 2D and 3D convolutional neural networks, a number of different approaches to actually map between what happens in the game from pixel information to annotated arousal of those videos. And we had about 50 videos to process. And in this particular example, we use classification. So we're trying to predict whether the arousal of a player of a particular frame, let's say, is high or low, given the pixels of the frame and the annotated trace that you see over here. I hope that you're able to see my mouse. So these are the convolutional neural networks that we use, like one of them. So basically goes all the way from frames to high and low prediction of arousal. So the result is quite fascinating because you can do that with up to 90% accuracy, which is the first time that such a thing happens within affective computing studies, because usually in affective computing, you take into account what the user is doing, like the facial expression of the user or the physiology of the user. But we don't really care about that. So this is like some form of user agnostic, let's say, approach to modeling emotion. But as I said before, we assume that basically the emotion is embedded in the video footage that we get from players. So what you see here is the activation maps that we get from play during the neural network activation maps that we get, and the red areas indicate higher activation, the blue areas indicate lower activation, and what you are able to see from the difference between high and low classes of arousal is that when arousal is high, the network tends to look at areas of the UI, such as the score and maybe the bar, the health bar down here, and obviously what's going on around the area of the player. Whereas in the low arousal classes, the activation map showcases that the network focuses on the timer, like how much time is left. So all these are quite interesting results and very informative of what's going on with regards to player experience just by looking at pixels. Now, a very recent example actually that was just published, is not out yet. In the next few days, the final paper will be out, is another collaboration or in-house, let's call it in-house research that we did in Model AI with regards to engagement prediction, to moment-to-moment engagement prediction of Twitch videos that we are able to find of a very popular game called PUBG. So basically, we went through a number of different streamers that stream on Twitch. We looked at how their audience corresponds to what they do during the streaming procedure. And we came up with a proxy of viewer engagement that we try to model on one end. And on the other end, we look at particular things that they do during the gameplay. And it turns out that we can actually predict the real-time, the moment-to-moment engagement of each video with very high accuracies across any streamer out there. And so in a sense, you can submit your video to us and we can tell you how your engagement line looks like in this in PUBG when you play PUBG. So these are the exciting things you can do with player modeling, but you can go one step further, and you can actually start investigating whether particular models that they're building very different games can be general enough in other games. So to which degree the input and the output of such a model can actually work and operate well and be accurate in very different games. And we did some initial studies here with Elizabeth Camilleri and Antonis Liapis in trying to actually predict arousal across very different games. And it turns out that you can actually do that with quite substantial accuracy, even though the problem is arguably very hard. I mean, we looked at these very different games, and as you see, a model that is able to predict how well you're doing in this sort of 3D maze game, and at the same time being able to predict what is your arousal in this horror-like game is a arguably very difficult task, if we assume that emotion is general, right, and can be predicted in a general fashion. So in the last part of my presentation, I just I just want to take you through a number of examples within what we called with Julian the experience-driven PCG paradigm, because that one actually fuses together the player modeling efforts with the procedural content generation efforts, in the sense that experience-driven PCG looks at the content as a building block of experience. So basically, what I want to show you here is an interesting example of evolving levels for Super Mario, so that levels look as believable as possible, or the agent in this particular case looks as believable as possible. So what you see here is two different videos of an A-star playing Super Mario Bros. But what we do basically is to evolve a level around the A-star agent so that the A-star agent looks as believable as possible. So we have a surrogate model of believability that maps particular parameters of the level to believability. So then we can actually evolve the level parameters to maximize for believability of not only an agent, but a human, right? So this comes in line with the recent discussion about, to which degree we should co-evolve agents within games and their environment. Obviously, both are important, and to which degree we can actually challenge more AI agents by offering more challenging testbeds. In this particular case, we don't offer more challenging testbeds, we offer more believable testbeds to test for their believability capacities, let's say. Finally, I think that should be my last example, and I think we're doing well with regards to time. So in this example that we called Sonasia is another example of what we call orchestration within PCG. So basically we use evolution to evolve both levels of a game and sound effects of a game. So essentially you have a designer that picks a particular tension curve, let's say, for a horror-like game. And then the system, the evolutionary procedure, creates a mansion-like, as we will see, a mansion-like level and places particular sound effects so that the combination of rooms and sounds meet the particular tension curve that the designer is placing. So let me try to play this video, and you will hear some weird sounds now, hopefully. It's like horror-like. So this is a level, an example of a level. You walk around. I don't know how loud it is. Maybe it is. Yeah. So we haven't tested this before, so I don't know to which degree you can hear me well, or you can hear the video, or maybe I should just stop talking. You can just hear the video.
I hear both you and the video.
Thank you, Julian. So, yeah, so basically, yeah, as you might have guessed, the evolutionary procedure here places a different sound effect for each room, like this riff that you have here, or some sort of sound effect in this room. But first, it actually designs the architecture of the mansion, and then on the second phase, it places the sounds so that the desired tension curve is actually achieved. Right. Yeah. So these examples just give you an idea of what is possible within AI in games with a particular lens through evolutionary computation. And I guess the two colleagues of mine here would agree, at least collectively, what you've seen today is that, and what we've argued in several of our papers, is that games, for all the reasons that you saw, actually, games could be seen as the last frontier of AI. I mean, they challenge AI algorithms to play them effectively. They challenge AI algorithms to play them believably. They challenge generative systems in the sense of creating visuals, faces of players, or even combinations of music, text, visuals, and so on. And they are also very, very challenging in the sense of effective computing, trying to actually model what these users in this sort of very rich human-computer interaction mode are doing. So collectively, games are really, really difficult when it comes to AI. But then again, AI can be the next step of games. And here we stand, being associated with the company Model AI. All of us work, the three of us work in a university. And I think we all believe that we can use all these techniques for playing games, for generating content, for modeling players as methods for advancing game design and game development at large, and even testing games, as you have seen in several of these paradigms and these examples. These are some suggested readings, but of course, you have seen so many papers in this presentation, so you can just go follow the references. But if you want to follow the book of Artificial Intelligence in Games, we have basically been covering parts of chapter 3, 4, and 5. My final note is that we all represent here, Sebastian, Julian, and myself, a community that focuses on games and cares about games, not only within the perspective of AI, but any technical perspective or any technical angle lens that views games and games research. This is represented by the IEEE instructions on games that Julian is taking care of as an editor-in-chief. And the corresponding conference, or let's say the sister conference of the journal, is called the IEEE Conference on Games. So if you want to get involved, follow us, submit your papers there, and hopefully we'll see your submissions. Final note is that Model AI, with all of us here, organizes this Artificial Intelligence and Games Summer School. This year was postponed because of the madness that we all experienced, but next year is happening, hopefully, in Copenhagen. The IEEE Conference in Games is also happening in Copenhagen next year. So if you're interested and you want to know more about AI and games, you can just follow us there as well. So that's all from my end. Maybe you want to have a final word, Julian and Sebastian, or just stop the recording here.
I mean, everything that Georgios said. I agree with everything Georgios said and what Sebastian said. So thanks to everyone for coming to our tutorial, whatever it means to actually come to a virtual pre-recorded tutorial. If you're watching this as part of our GECCO offering, it will be available after the tutorial to take questions. And if you're watching this in some other way, we're looking forward to interact with you and engage sometime in the future.
And hopefully see you in person in Copenhagen.
Right, hope to see you in person in Copenhagen. It's a good place. Right, thank you. Bye.
Bye.